6.1, this is back to differential equations now. We're using the other book. Is on page 319, talks about basic theory of linear differential equations. Consider the given initial value problem. We're talking about a second order differential equation. The key is to make that a 1. Then you could read P of t, Q of 2, and G of t. Assume that those three, P, Q, and T, and G, are continuous functions on an open interval containing and that's what makes this an initial value problem, if those are the same. If those are not the same, that will be a boundary value problem, which is a lot tougher to deal with. The problem, we're talking about this problem, has exactly one solution, and the solution exists throughout the interval I. So this is called the uniqueness theorem, really. Now this could be generalized. I can generalize this. I'm going to put that right here. Can generalize this to y triple prime, the fourth derivative, and the list goes on. But I need as many initial value problems. The deal is the same idea. As long as that's a 1, I want all of these functions multiplied by y and its derivatives, including the g function, to be continuous. So if I glance at number 2, and this is on page 326. If I glance at number 2, determine the largest interval for which theorem 1 guarantees the existence of a unique solution. We did this already. This was in your first test. So what we do, we glance at this, we say, all right, you know what, let's see, are there any conditions? Any conditions on any of these values? Well, let's see. We want what? We want to make sure this is a 1. If this is a 1, that's P. Q is 0, and that's G of t. Or vice versa. It doesn't matter. So when I look at those, I would notice that this is restricted by a radical. The radical indicates that you can only be to the right. And since pi is in there, the biggest interval I can get is 0 to infinity. Now, how come I didn't include 0? Open interval. How about this problem? Well, the key is to make that equal to 1, so this is really y triple prime minus 3x over x into x plus 1 y prime plus y over x into x plus 1 equals 0. This simplifies, not that it matters. So those are continuous as long as x does not equal a 0 or a negative 1. So those values you're not allowed to have. What's going to restrict? The initial condition. Where's negative 1/2? Negative 1/2 happens to be right there, which means the biggest interval I could have is negative 1 to 0. I'm guaranteed on that interval I will have a unique solution by theorem 1. Again, we did this on exam 1. It's already there. This is the second time you're going to see this. And how does this work? The same deal. The goal is to make sure that's a 1, that's not a 1. We could say y triple prime plus e to the x over x squared minus 1y equals natural log of x over x squared minus 1. We want all of these functions to be continuous, which are what? This and this. Well, to start off, this restricts x to be greater than 0. This says stay away from 1 and negative 1. So far, the green part take away 1. What's gonna really limit your choices would be, where's the initial condition? All of these are the same, that's why this is an initial value problem. 3/4 is right there. So the biggest interval I can get in this case is 0 to 1. And you could see how challenging that would be if y of 3/4 equal 1 and y prime of 5/4 equal 1. Then you will have a boundary value problem. You'll create a rectangle, and that becomes a bit more challenging than you think. Now, another idea in this section that's extremely important for us is the famous Wronskian. Given a list of functions or variables, it doesn't matter, let those be n functions and they are n minus 1 differentiable, times differentiable. The Wronskian of those is simply you list them out and you take a derivative, another derivative, another, and another, all the way to n minus 1 derivative. And if you recall what this stands for, the absolute value in matrix land, that's determinant. You find the determinant of that matrix. And this is called the Wronskian. And it's so important they gave it a name. Why is that? Because if the Wronskian, and this is how I remembered it, if the Wronskian does not equal 0, those functions I listed are linearly independent. Right? We did this already. When you wanted to find the determinant of a matrix, if it doesn't equal 0, then remember invertible part? Kind of like that. And here we are. I have two problems for you. It says determine whether the given functions are linearly dependent or linearly independent. Well, the best way to do this, I mean, of course, you are welcome to say c1 times x2 plus c2 times x squared minus 1 plus c3 times 5 equals 0. See if c1 equals c2 equals c3 equals 0. That'll work, right? Or simply the Wronskian, and I'm going to give you a secret about a Wronskian, by the way. The Wronskian is given by, list them, x squared minus 1 and a 5, derivative, derivative, and a derivative, 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 and a derivative. And if I want to find, I will probably take because of the zeros, so that's positive 5 times, and you cross its row and column if you recall how that works, and it's simply this minus this, 4x minus 4x. Isn't that a 0? Therefore, linearly dependent. So if it doesn't equal 0, it's linearly independent. That's how I remembered it. Now, the point that most students don't pay attention to, the Wronskian evaluated at a point. The one catch, you don't want the point to make all of these zeros. I suggest you keep it simple. Don't worry about evaluating that at a point for what we need, but maybe in future classes. This is the cosine of 2x. This is the cosine squared of x, and this is the sine squared of x. So one derivative is negative twice the negative twice the sine of 2x, and another derivative, negative 4 the cosine of 2x. Okay, and if I take a derivative of this, let me give that a bit of stretch. So if I go by cosine squared of x, derivative of that will be twice the cosine of x times negative sine of x. Wouldn't you say that's negative the sine of 2x? And another derivative will be negative twice the cosine of 2x. And twice the sine, oops, I'm taking a derivative already, forgive me. If you take the sine squared of x, a derivative of that is twice the sine of x times cosine of x, which is the sine of 2x, and a derivative of that is twice the cosine of 2x. So I'm really looking at, if I want the Wronskian, I'll pick a row or column, or I could list, if you remember the shortcut, I could list a cosine of 2x, a cosine squared of x, a negative twice the sine of 2x, a negative sine of 2x, and a negative 4 cosine of 2x, and a negative twice cosine of 2x, and I could proceed. Or I could say, you know what, how about the Wronskian evaluated at 0? Since that doesn't make all of them 0, that is 1, 1, 0, 0, negative 4, 0, negative 2, 0, and a 2. Isn't that much simpler? And if one of the rows is 0, doesn't that guarantee that this Wronskian is going to be 0, therefore they are linearly dependent? Just be careful with this, not to overdo it. It can't make the initial all 0, and then you'll be okay. And there's the homework on this section. Everything shifted, I'm not sure why. There we go.